So thank you, Guru. That was actually a quite entertaining introduction. As Guru said, actually I'm waiting. Okay, so I am going to talk about the future of networking and the past of protocols, and this is joint work with Martin, obviously Teemu, Nick, and many other people. As Martin had on his slide, there are dozens and dozens and dozens. So we're all gathered here today to talk about software-defined networking. And I think it's a pretty clear consensus that software-defined networking, or SDN, has advantages over the status quo. That's not really what we're debating. But the question that's in many of our minds is is this somehow the right answer, or is this some stopgap that we're going to believe in it for a couple of years, and then 4 or 5 years from now, there's going to be another idea that's going to sweep the thing, and the Guru and Dan are going to organize another workshop on something else. And so the question is is SDN the right solution? Is there some fundamental sense in which this is the right answer? And so my talk is not going to be about what SDN is, about why it is. It's why we ended up here. And so remember when Dan opened up this conference and he made some slightly derisive comment about the philosophy of SDN? That's me. That's what I want to talk about, how we ended up in this place. And I hopefully will argue that it is the right answer for some fundamental reasons. But before we do that, let's remember what made networking so great, in particular what made the internet so great. So it's really layering. We could build applications on top of reliable transport, on top of best effort global delivery, which is on top of best effort local delivery, which is on top of physical transport of bits. Okay, we all know that, right? And we knew that in the first time we took networking. So but why is it so important? It's important because it decomposed the delivery into these fundamental components. If you sit down and you actually think about, okay, how do I actually get bits from here to there? You will rediscover that, actually the layering gets it exactly right. These are the fundamental components you need to think about. And so what do those fundamental components give you when you break up the problem that way? It enables innovation. It enables innovation, that you can innovate in separate pieces of the architecture independently, but keep a coherent system. And just to dial to the end of the talk, when Martin described the value proposition for SDN, it's all about innovation. That's what the value proposition of the internet was. That's why this technology took over, is because it enabled innovation. So it was an amazing success. However, and this may not be of concern to most of you, it is to me, it is an utter academic failure. We built an artifact, we did not build a discipline. So there's no denying that the internet and networking in general has changed the world. However, when you think about it as an academic discipline, as a thing that we study, it does not match up against the other fields of computer science. If you compare it to operating systems or databases or distributed systems, in those fields, you teach basic principles. Fundamental results on distributed computing and Paxos and Byzantine agreement. In networking, all of us, we teach a big bag of protocols. We try and make it entertaining, but we have no principles to teach. The other systems, computation and storage, they're easily managed, largely because of virtualization, that we know how to manage them. Networks, I don't think I need to say anything more. And then, you would say, well, the software systems, operating systems, so they're so widely deployed. How could they continue to evolve? But they do. We've had Ruby on Rails. We've had Apple's iOS. We've had Android. There have been major changes in the last 10 years in software systems that it's actually, when you step back, it's remarkable to think for as many devices that have software on them now, you would have thought that they would have had hardening of the arteries and been slow to innovate. But they're trucking along. They're continuing to innovate much faster than networking is. So when you look at this, you wonder, so why is networking lagging behind? What is it about networking? We have a large community. We have a very large networking academic community. We publish more papers than anybody. So why are we not able to get our act together? So to think about this, let's go back, and this is retracing some of the history that Martin described. The networks used to be very simple. IP is an incredibly simple protocol. Ethernet is a beautifully simple protocol. What could be simpler than this? But then we started to get, because of the success of networking, we started to get all these new control requirements, that all those fields that Martin talked about, the sort of the state that we had to manage by hand, we had all these control requirements that led to a great amount of complexity. And that's where we went off the rails. Now, fortunately, the infrastructure still works. I mean, I'm not complaining about how networks work today. They work just fine. But they work because you, not me, this is not my skill set, but your skill set, are terrific at mastering complexity. You talk to somebody who operates a network, they can drill down to the lowest levels imaginable. It really is quite startling how much you have to keep in your head in order to keep a network working. So our field excels at that. We know how to master complexity. But that is both a blessing and a curse. Okay? So let me tell you a simple story about complexity to illustrate why it's both a blessing and a curse. So my first non-academic job was working at Xerox Palo Alto Research Center. And I joined Xerox PARC in the mid-'80s. And at the time, it was the mecca of user interface design. You know, sort of PARC, not me, well before I got there, but PARC had invented all the sort of personal computer, the user interfaces and so forth. So it was the mecca of user interface design. And around 1985, Don Norman, who was a user interface expert, probably the most famous person at the time, I think he worked at Apple then, came to visit PARC in around 1985. And so there was a lot of excitement at PARC. You know, here was the person who sort of made these ideas, made them, you know, sort of enter the marketplace successfully, coming to PARC to talk about it. The auditorium was absolutely packed. And so Don Norman, who sort of was a very distinguished-looking gentleman even back then, sort of knew how to do a stagecraft. And so he keeps us waiting in the audience for a while, and then he slowly walks out on stage. And he walks to the podium, and we're all just waiting to hear what he has to say. He says, "Who here drives a stick shift?" So we all look at each other like, what? And he says, "No, I'm serious. Who here drives a stick shift? Raise your hands." And so a few of us raise our hands, and then more and more. And you know, it's an engineering audience, so we're really proud that we drive a stick shift. So pretty soon, you know, 80% of the room's got their hands up. And so he just calmly looks at us, and he raises a finger and says, "None of you should ever design a user interface." So what was his point? His point was that the ability to master complexity, meaning drive a stick shift, is not the same as the ability to extract simplicity. And that's what you do when you do a user interface design. Now, when you're first designing a system, mastering complexity is necessary. You got to do it. Everybody thinks it's valuable. That's right. But when you're trying to make a system easy to use and easy to understand, that's about extracting simplicity. And the point that he was driving home that day over and over again was, you will never succeed in extracting simplicity if you don't at least recognize that it's a different job than mastering complexity. So if you like driving a stick shift, don't you design user interfaces, get a different job. Because you like complexity. So you don't want to design systems for people who don't like complexity. So that was his point. So why am I telling you this story? What's my point? So my point is that while networking has done many great things, we have never made this important distinction between mastering complexity and extracting simplicity. And because we've never recognized the distinction, we've never made the transition. We're still mastering complexity. The people who understand complexity the best are the kings of the hill in our kingdom, right? And we don't put much emphasis on extracting simplicity. And you know, that has practical ramifications, which I'll talk about, but it also has disciplinary ramifications, which is extracting simplicity is what builds the intellectual foundations. If you talk about the principles that these other fields have, they're all about having boiled the problem down to its sheer essence and then being able to describe it. We don't do that in networking. We don't have those principles, and it's because of this. So what are other fields that have made this transition? So let's take a simple example. Programming. Programming has been terrific at starting off its roots, machine languages. My God, if there was anything that was about mastering complexity, this was it. Okay? And then we developed some higher level abstractions, you know, operating systems abstractions and so forth. And then we have modern languages that have object orientation and so forth, much higher languages, much more simple to program. So the essence of extracting simplicity. And the lesson we learn here is that it's really these abstractions that are key to extracting simplicity. It's the abstractions they used in programming, and it's going to be the abstractions that we have to use in network. Now, many of you might have heard this talk by Barbara Liskov, the Turing Award winner. She goes around giving this talk on the powers of abstraction, and she has this pithy saying, which is, modularity based on abstraction is the way things get done, which translated means we as a field have one trick, which is if we want to build a system, we use abstractions which lead to modularity. That is, we define some abstractions, that leads us to some interfaces, those interfaces lead us to a modular system, and it's only by having a modular system we can write a system of tens of millions of lines of code and actually get it to work and maintain it and reason about it. This is the trick we have. This is what keeps us all in business. So the question is, what about the abstractions in networking? What can we do there? So I started off the talk by talking about the great abstractions we have, which is layering. But layers only deal with the data plane. And as Martine described, where we got into trouble was in the control plane, all these control requirements. We don't have abstractions there. We don't really have any systematic way of thinking about that state. The same way we do have about thinking about data delivery, we don't have about managing control state. So how do we find those abstractions? It's very simple. This is what you always do when you're charged with finding abstractions, which is you define the problem and then you decompose it. Okay? So our problem is network control. So how do you define that problem? It's pretty simple. What do you do when you're trying to control a network? You are trying to compute the configuration, that is, mean the state, in every physical device. You know, that's forwarding tables, that's ACLs, whatever. That's the control problem that Martine described. Right? Now, we can't do it in a fully general sense. We have some constraints. We have to realize that we operate without communication guarantees. I mean, it's our own network that's doing the communicating, so we can't rely on it being perfectly reliable. We have to deal with delays. We have to deal with drops. We also have to live with the constraint that we have a given network level protocol. If your protocol, like IP, doesn't have a packet header for the thing you want to communicate, you're out of luck. You have to live within the limitations of what the fields in the packet header are. So this is what our field has been doing for years. And we just think, okay, this is our job. And we think that way because we're good at mastering complexity. Because only people who love complexity would find this to be a reasonable request. Everybody else in the world, if you pose this question, would say, you are absolutely nuts. Let me give you an analogy to convince you. Let's take a programming analogy. I'm going to go up to a programmer and I'm going to say, please, you have to write a program that specifies where every bit is stored. That's a little bit like telling me what every forwarding entry is in the network everywhere. You have to do it, and you have to explicitly deal with all internal communication errors. That's like we have to deal with arbitrary delays and drops in our distributed systems. And you have to do it with a programming language that's not very expressible. We're going to give you COBOL. Okay? So, if you gave that to a programmer, the programmer would immediately say, no. Say, first, let me redefine the problem. I'm going to define a higher level of abstraction for memory, so I don't have to worry about where the bits are. That subsystem will. And I'm going to define some reliable communication primitives, so I, as the programmer, don't have to worry about that. And by God, I'm going to define a more general programming language. Okay? That would be the first thing a programmer would do. Say, I'm going to redefine the problem. And then once you've done this, this is introducing 3 abstractions. And once you've introduced these abstractions, you've divided the problem into tractable pieces. You can define reliable communication protocols. You can define abstractions for memory. And once you've done all that, you make the task of writing the control program easier. It's not trivial. If your control program was to compute k-shortest paths that only had certain kinds of overlaps, it might be a hard computation, but it's inherently hard. It's not made more difficult by having to keep track of all the communication errors and so forth. So that defining these abstractions are the way you get rid of these extraneous difficulties, and you're only left with the inherent difficulty of the problem at hand. So now let's apply this to networking. So we're going to go from the requirements that I talked about in the control program to the necessary abstractions. So the first one is we have to operate without communication guarantees. That means that we have distributed state and that we have to somehow deal with it without having any guarantees about the communication. And what that means is we need, in order to not have to For us to worry about, we need to define an abstraction for distributed state. So the programmer doesn't need to worry about it. We've got an abstraction for that. The second thing is we need to compute the configuration of every physical device. That's our fundamental problem. So we need to come up with an abstraction that simplifies that so that we don't need to think about every device. We just can think at some higher level that makes it easier to specify the behavior we want. And then we have to operate within a given network level protocol. And there, we need an abstraction that gives us a generalized forwarding plane rather than some specific forwarding model that was given to us. Okay? So these are the three abstractions we need to face. So let me talk about them briefly one by one. So the distributed state abstraction, what you want to do is you want to shield mechanisms from the vagaries of distributed state. Crazy things can happen. You need to deal with the state. You just don't want to deal with the fact that it's distributed. So there's a very natural abstraction that comes out of this, which is I would just show you the state. I give you a global network view. That's the state you needed to deal with. I'm just going to say, here's a graph. Here's the network. It's annotated with all the metadata you want. I'm going to give it through an API. And then if you want to use it, you now just program to that API. You're not writing a distributed protocol. You're writing a program over a data structure. Okay? So you're using Dijkstra, not Bellman-Ford. Now, as Martine noted, this is an oversimplification. I've described it as making it logically centralized. And you could. But the point here isn't that you have to make it centralized. It is that the distribution model is your choice. It's not the network's choice. You have hidden the distribution in the network. You now can distribute it based on your scalability requirements, your resiliency requirements, whatever you care about. But it's not based on the fact that I've got 10,000 switches out there and they all have the state that I've got to manage. Okay? So from now on, I'll just assume that it's logically centralized. The second abstraction is the specification abstraction. You know, when I'm writing a control program, it should express my desired behavior. It should not have to tell you how to implement that behavior on the particular physical network you happen to be running on. Okay? So the natural abstraction is some kind of simplified model of the network that is only complicated enough to allow you to specify what behavior you want. Okay? So this really is network virtualization. You want to provide a virtual image of a network, let people control that, and then what the real physical network is underneath doesn't really matter. So let me just give you a simple idea of what I'm talking about here. Let's assume the physical network was this, some complicated topology, but I was trying to do access control. So what abstract model of the network would you give me? The abstract model is I'd give you a crossbar, because if the behavior I want to specify is A can or cannot talk to B, I don't care about all these switches. For specifying the behavior, I just say A can or cannot talk to B. It's somebody else's job to figure out how to make that happen in the real network. And then the third abstraction is a forwarding abstraction. And here, obviously, the control plane needs to allow for flexible forwarding. It doesn't want to be limited. So the abstraction should not constrain the forwarding behavior, but it should hide the details of the underlying forwarding hardware. That is, if you're going to get beyond vendor-specific solutions, you don't want to have to worry about what particular hardware you've got underneath. You want some higher-level forwarding abstraction. Okay. So you've been very patient. And so at this point, I'm now going to summarize my entire talk in one sentence, which is that SDN is those three abstractions. That's it. Those three abstractions are exactly what software-defined networking is, no more and no less. It's a distribution abstraction, it is a forwarding abstraction, it is a configuration abstraction, and you are done. So SDN is not just a random idea. It can be derived in this loose metaphorical sense from decomposing the problem of network control. And what this does is it gives you some confidence, at least gives me some confidence, that there's some fundamental validity and general applicability. Fundamental validity because it comes out of these arguing about what abstractions you need. General applicability because in arguing about those abstractions, I never once mentioned what the control problem was. It is anything that's trying to manage network state that has to do with forwarding falls into this category. So fundamental validity, general applicability. Let me talk a few minutes about realizing these abstractions. This will be showing the same pictures that you've seen 10,000 times before, but it'll give me some context for my later comments. So the core challenge is to make the distributed control problem a sort of logically centralized one. And as I said before, by logically centralized means the distribution model is my choice, not the network's choice. So to do so, I have to design a common distribution layer. That is, some layer that gathers the information from the network elements and then sends out control messages to them. And this is done, as we always say, by network operating system. And so here's the picture that we've all known and love. You know, you start off traditional control mechanisms, you have these individual routers exchanging pairwise messages, but instead in SDN, you throw those away, you define a network operating system which provides this global view, and I will say I stole these slides from Nick, so I don't know what he's going to give a talk on. And then you've got a control program over that global network view, and that can be routing, access control, whatever it is. Now, the key thing to recognize is that this is a major change in the paradigm. We are not designing distributed control protocols anymore. Okay? We are defining a centralized or logically centralized control function, which is the configuration is a function of the network view that I give you. And so as soon as that view converges, your configuration will converge. It's much easier to think about and much easier to reason about. So that means this spells the end for distributed protocols. But what is somewhat less appreciated is that this is the beginning of the software era of networking. And we all say software-defined networking, and yeah, we know that involves software. Software communities are different from us. They have different thoughts about what you standardize and what you don't. They have different thoughts about what a reasonable rate of change is. They have a very different culture. By adopting SDN, we have to become a software community. We're not anywhere close to that now, but that's where we're going to have to be. That was the first abstraction. Let me talk about the specification abstraction. Here, it's just a simplified model of the network. Control program is merely, you give me this simple model, I then have to configure that. And then we have this layer that takes you from the simple model to the actual physical topology and says, if this is the behavior you want on the simple model, I have to translate it to the actual physical topology that the real network has. So that means that in this nice picture, you now have to kick up the control program, insert a network virtualization layer, so that now your control program configures the abstract network view. Your network virtualization layer takes that and configures the global network view, and then your network operating system actually communicates that to your physical devices. So now the SDN picture has gotten a little more complicated so that you can actually simplify the act of writing the control program. And that leaves the third abstraction, which is the forwarding abstraction. And here, you sort of think switches have two brains. They've got an ASIC and they've got a management CPU. And your forwarding abstraction has to consider both, because they're very different. Interfaces is CPU, management CPU, who cares? We can do that 10,000 different ways. It's the ASIC abstraction, which is much more subtle, and that's where OpenFlow comes in. This requires a lot of careful thought. And I'm not going to talk any more about the details of the OpenFlow configuration, except to say the following. That when you say OpenFlow is the answer, what that really is assuming is that switches are the unit of forwarding abstraction. That's not necessarily true. You could say for a data center, for instance, I want the fabric. That is, the forwarding abstraction says I'm going to take it from one end and take a packet and deliver it to the other end. That's the forwarding abstraction, that we can build fabrics for data centers, and maybe that should be your forwarding abstraction rather than individual switches. I don't know which is right, but the point is they're both SDN. So I say that just to caution that we should keep in mind that as we debate the finer points of OpenFlow, that it's, as Martin noted, it's a detail in the overall SDN architecture. It's sort of down there and it occupies one small place. Because it is closest to the hardware, it is absolutely crucial for the industry. I'm not diminishing its importance at all. We need to standardize it. We need to understand it. We need to get it right. But architecturally, it's a minor piece. And the only reason I make that point is we need to make sure that we don't let the tail wag the dog. And if the tail is OpenFlow, what's the dog? And the dog here is a clean separation of concerns. That is, in SDN, you have a control program that specifies the behavior on an abstract model. The only thing that control program thinks about is what does the operator want. That's it. You don't think about anything else. You then have network virtualization that says, I don't know anything other than I've got this abstract model that's been configured, and I have to translate it into a real physical topology and figure out how to make that mapping coherent. And then you have a network operating system that says I have this fully configured logical map of the network, and I now have to transfer that into the actual physical devices. Each piece of this architecture is a very limited job, something we know how to do, that doesn't involve the overall picture. Okay? Now, there are 2 points I want to make here. One is that, as Martine said, innovation is the true value proposition of SDN. And then going back to my second slide, the reason why the internet was so successful is because they had these layers of abstraction that gave you separation of concerns that enabled you to innovate in these separate layers at the same time in a compatible way. That's what SDN does. It builds this ecosystem that we can have progress going on in all of these pieces in a way that maintains an overall coherent system. That's the value proposition of SDN. So there's this tie between abstractions and innovations. It's very fundamental, and it is core to why SDN is the right answer. Okay, so in my remaining -2 minutes, let me just say a few final words. The future of networking lies in finding the right abstractions. You know, this era of defining a new control protocol every time you have a new problem, that's over. It's going to take years to internalize and evaluate abstractions. It's taken every other field, from operating systems and distributed systems, from the time they come up with their first ideas to the time they sort of decide that this abstraction is right. It's going to take a long time. But what's going to take even longer is for us to adjust to the fact that software is king now, that it's going to be a software-oriented culture that's going to rule our field. And that's going to be harder for us to deal with. And lastly, we are in the early stages of an intellectual voyage. We should keep our minds open. That I know how far we've come in our thinking in the past 4 years, and if we go as far in the next 4 years, things will look very different than what we think now. They won't be different in the sense that we will think we were wrong now. We'll just think we were naive. And on that note, thank you.